Welcome to the third presentation in Unit 6 entitled I'm Rubber, You're Glue. So it says I'm rubber, you're glue, whatever you say bounces off me and sticks to you. So the learning goals are that students be able to identify reflection, refraction, and diffraction at a boundary and give everyday examples of each. So here's what we already know. We know that waves can reflect when they hit a boundary. You see that every day when you look in the mirror. You see the light reflecting off the mirror. There are two specific types of reflection. One is called open and one is called closed, or excuse me, one is called fixed. And the other was that when waves propagate, they go in straight line directions. In other words, the wave, no matter what it's doing wave-wise, goes in a straight line this way, or it can go in a straight line this way. Now, here's what we learned in the lab, that waves can refract when they hit a boundary. Waves slow down when they enter a different media, and they can diffract when they hit a boundary as well. So, reflection is a wave hitting a surface and it always reflects off the same angle. And that's what we call the law of reflection. Now, generally when we refer to the law of reflection, we're not referring to this angle right here. That is not what we're referring to. Instead, scientists draw a straight line down from here and they call that the normal line. It's called the normal line because normal is the same thing as 90 degrees. So when you draw this normal line down, the angle is actually measured from this middle line. So you see this right here is called theta I. Now theta stands for an angle. You might have seen that in maybe a math class. So theta I stands for the initial angle. Theta R stands for the reflected angle, and those values have to be equal. So the question is why do we measure the angle from this normal line as opposed to this line right here? Okay, these angles are the same as well as long as the mirror is flat. But the law of reflection we want to hold for curved mirrors as well. So if you have a curved mirror, it's real important that you be able to say that the law of reflection works. So by drawing that middle line, that normal line, it always works, even when you have a curved mirror. Everything you see depends on the fact that light is reflected off of it. Unless it emits light, like it glows in the dark, or it's the sun, or it's a light bulb, the reason why you can see it is because light is reflecting off its surface. It's also really important that you understand that when a shirt is blue, it's blue because the blue light is reflected, and all other colors are absorbed. You can actually use this idea to say, okay, if it's really hot outside, I want to wear a white shirt. The reason why I want to wear a white shirt is a white shirt is the kind when all colors of light are reflected. If all colors of light are reflected, then there's no heat that's generated whenever it's absorbing light from the sun. Okay, there are lots of uses for reflection, including some that you use every day, like mirrors. Okay, and some that you don't see as often, which is echolocation, that's what bats use, sonar, and fiber optic cables. Fiber optic cables are what we actually use to produce really fast internet. Mirrors actually reflect electromagnetic radiation, not specifically only visible light. You can have a mirror be a curved mirror or a flat mirror. In both cases, you see these mirrors are curved. And you may be thinking, well, that's a satellite dish, that's not a mirror. Well, that's not entirely true. What it is, it's a curved mirror. And what happens is whenever radio waves or microwaves or whatever a satellite dish uses hits the wave, it actually reflects them to this particular point right here. And it concentrates the signal of that to this particular point, which is then taken and it reads the signal as your television or whatever signal that is. Okay, so mirrors don't only have to be visible mirrors. You can use them for radio waves and microwaves and all sorts of things. Although the most common ones are visible mirrors. In order for them to reflect visible light, however, they have to be highly polished. And generally speaking, they have to be made out of things like glass. You can't take a plastic like this and make a mirror out of it. Okay, fiber optic cables are also use the principle of reflection, and what these are, they are clear wires that allow light to travel through them. Their the outer interior. So this particular part of this fiber optic cable, this plastic coating, on the inside of that outer coating actually has a substance that allows light to reflect. And what that does is it allows you to send light down these particular wires. The reason why you do this, the reason why fiber optic cables are better than traditional wires, is because light is a lot faster than charges. So you can send signals a lot faster than you could on a traditional wire. That's why high-speed internet always talks about fiber optic cables. Okay, echolocation. Animals emit sounds, and that sound can reflect off an object. And whenever that sound reflects off the object, okay, it comes back to the bat. The bat can detect that signal, and by measuring the time between the signals that it gets, it allows the bat to see in the dark. Okay, so a bat can actually use echolocation to find something as small as, say, this moth in a cave in which there is no light. Okay, sonar stands for sound navigation and ranging, and it's basically our technology or our boat's version of echolocation. What we do is we send out sound pulses, and we wait for those sound pulses to hit something and then reflect back. And when those sound pulses hit and reflect back, we can measure the time and frequency of those particular pulses, and that will actually allow us to see underwater. So we can detect what's there using sound waves. So an example of this is whenever you see this boat, it sends a signal down to the surface, and it can actually time how long it takes to come back. Whenever you measure this particular time, we know that sound travels in water at about 1,500 meters per second. As a result of that, we can say, okay, if it took 2 seconds for us to detect the signal had to go down and had to come back. So if I want to know how long it took just to go down, well, if it went down and back in 2 seconds, that means the entire trip took 1 second. And then I would have a time. And then I would have the speed of this particular sound wave, and it would be 1,500. And then that would allow us to do a calculation to solve for the distance. And we will be doing those calculations because we've done speed equals distance over time. Okay. There are two specific types of reflection, and one is called open reflection, and that's where this right here, whatever it's reflecting off of, is free to move. So as you see, as the wave approaches this part of this boundary, the boundary is free to move, and so it comes back up, and the pulse reflects on the same side. You also have a fixed reflection, which is what happens whenever you hold this particular end of the slinky, and whenever you generate a pulse. Okay, it goes up, but then it has to invert and come back down on the opposite side. So what is the law of reflection and when does it apply? The law of reflection is theta I equals theta R, and it always applies to mirrors or to reflection. So whenever light or sound or any sort of wave strikes a surface, it will always bounce off at the same angle. What is angle theta? Okay, so this is not drawn to scale. Remember, this is a normal line or a 90-degree line right here. So the first thing that I can say is that this particular angle right here is 70 degrees. Because if this is 90, 90 plus 20 have to be 70. So because of that, I know this is 70 degrees right here. The law of reflection says that this angle, this theta I and this theta R have to be the same. So this one right here has to be 70 degrees. If this angle and this angle have to add up to 90, then this is 20 degrees right here. So these two angles end up being the same. Now, why did I not just go directly from this 20 and say that this is 20? And the reason why is because I wasn't sure if this would work exactly. This is the only place that the law of reflection works. If you were to have a curved mirror, that would mean that these two values don't have to be the same, but these 70s do. So you always want to measure from this 90-degree angle line. It says a boat sends out a sonar pulse at 100 or 1,500 meters per second, receiving a return pulse after 180 seconds. How far is the boat from the object it has detected? So the first thing I want to write down is I want to write down the fact that I have a speed of 1,500 meters per second. Now, if I want to draw this out, when I send the sonar pulse out, it goes down it strikes the surface, and then it comes back. Because of that, the 180 seconds is not the time that it required to reach its target. Instead, the time would be the 180 seconds divided by 2, because it had to go there, reflect, and come back. So it actually traveled this distance twice, or it took half the time to get there. So now that I know that this is 90 seconds, I can solve for the distance. So I would say speed equals distance over time, or 1500 equals d over 90. At this point, you would solve for d by multiplying both sides by 90, and when you do that, you end up getting a pretty large value of about 135,000 meters, okay, which is pretty far. Next, it says design an experiment in which you test light to determine if light striking a mirror is open or closed reflection. So the difference between open or closed, or sometimes this is called fixed reflection, is you want to measure the pulse. So you would set up a system in which light struck the mirror at a certain orientation. So all the light struck where crests hit the mirror. And then what you would do is you would have a detector right here. And the detector would say, does this thing come back as a crest or a trough? If it comes back as it starts as a crest and it ends as a crest, that's an example of an open reflection. If it starts as a crest and goes to a trough, you would say that is a fixed or a closed reflection. Okay? Not only can light reflect, but light can refract as well. Refraction is the bending of a wave as it changes from one media to another. So for example, remember media means what it's traveling in. It could be going from air to glass. Well, when light travels from air to glass, it actually bends. And you can see that pattern between these two. You can see it in this pattern, and you can actually see it when you write it as a vector. Now, refraction is whenever the light wave bends as a result of going to a new media. What happens is the original wave, actually different parts of the wave strike the boundary at a different time. So here this is traveling with a certain speed, say it's 100. And as it goes to the new barrier, it slows down to 80. The problem is based on the orientation of the barrier, this part of the wave right here is going to slow down first. So it slows down to 80. Well, this is still going at 100. As a result of this thing, it will actually turn. You can see the idea behind refraction if you're pushing a lawnmower. If you're pushing a lawnmower and you have two wheels that are on the concrete, and then you have two wheels that are on the grass, and you just kind of push it and let it go, what happens is the wheels will go faster on the concrete than they will on the grass, and so the lawnmower will turn towards the grass. Okay, so waves will actually slow down or speed up as they enter new media, and then we say that it turns based on the fact that there are different speeds that are there. Now, refraction is actually very useful as well. Glasses use refraction. The fact that as the light goes from the air to the glasses, you can actually bend the light. And we can bend the light to a specific point so it goes to the right point of your eye and you can see even if you're nearsighted or farsighted. Prisms that are used to actually create rainbows are examples of bending white light and separating it into the colors of the rainbow. Your eye actually works on the same principle. Telescopes work on the same principle. Even the design of glasses work on this particular principle. If you ever go to a restaurant and they have a glass that it looks like there's a lot of stuff in there, but it's actually bending the light and there's not very much drink in there, that's exactly what they do. Is they design the cups to make them look like there's a lot in there, even though there's really not. So glasses can bend light and they can focus light on the correct part of the eye. So if you look right here, this is where you want to get the light to be. Unfortunately, some people are nearsighted, some people are farsighted. So as a result of that, it focuses the light on the wrong point, either here or behind it. What glasses will do is they will bend the light to get it to the correct part. Now the same principle is used in laser eye surgery. What they do is they reshape the lens here to change the shape of the lens so that it focuses the light on the correct point. A prism is used to bend light. There's an uneven surface, and so since you have this triangular surface, different parts of the light are going to hit it at different times, and therefore it's going to bend and separate the different colors of light. So prisms were actually used to detect infrared and ultraviolet light before we could detect them in other means. So you can actually hit the prism, you can measure the fact that there's something above purple and something below red. It says refraction is, it should be the bending of light as it passes from one media to another. It says as light travels from glass to air, the light increases speed. So what will be the direction that it bends? Now, if you notice, um, whenever the light ray travels from air to glass, it actually bends kind of towards the glass. And that's because of the fact that it's striking the wave and it's slowing down. Whenever it slows down, it bends in that particular direction. So what this will actually do is it actually take its original value. So if you were to take this straight line that you have originally for the light ray and shift that same line down there, it would be the same direction of light on the other side. It says myopia is considered a common condition, commonly known as nearsightedness. How would you correct this? And the idea is you would put a lens in front of the light and you would refocus the light to hit the correct part of the eye. And so what you would do is you actually set it so that when the light comes in, instead of it focused to the wrong point, it would actually focus here. So you're actually extending it so the light doesn't focus quite so early. This is what material is the most dense. Whenever it bends toward the normal, so whenever it bends towards this line, it's going to be more dense. So if you look at this, we have to reverse this particular direction. If it was going this way, it bends towards the normal. So we would say that this right here is the most dense material. So it's water, or it's glass, or it's a diamond as opposed to air or a vacuum. Okay, the last thing we need to talk about is diffraction. And diffraction is the apparent bending or spreading out of a wave as it encounters an obstacle. So we have a wave, and we have a small barrier in the wave with an opening. And what happens is it propagates a new wave. It generates a new wave that comes through the barrier. Diffraction applications, or you can create things that are called diffraction gratings, and those are used by astronomers to look at different colors of light in telescopes. You can actually do the same thing with X-rays, and this is actually one of the very first pictures of DNA. It is a top-down look at DNA, so it looks like you just kind of have this X right here, but what it is the two strands of DNA looked at from the top down. You can also use diffraction to generate three-dimensional holograms, which you're actually starting to see a lot more of now, is they're actually putting on concerts of deceased celebrities using holograms. Okay, it says, how does diffraction differ from refraction? Refraction is changing the media. Okay, so you're having some sort of bending of waves as you go from air to water, water to glass, glass to diamond. Diffraction is bending when you have a barrier. So all of these things can be water. So it's water and water and water, but there's just a little barrier that makes me bend around that particular barrier. Okay, it says what wave phenomenon is responsible for the diffraction pattern on the wall. And if you look right here, there's a bright spot, and there's bright spots, and there's alternating dark spots. That can only happen when waves interfere with one another. But in order to generate multiple waves that allow them to interfere with one another, you have diffraction. So diffraction is how you create the multiple lights, and then they are allowed to interfere with one another. And when they interfere, you have the superposition of the waves that results in that pattern there.